Tá pensando ainda. So, welcome everyone for the next seminar on probability stochastic process from USP. And today we have Dirk Erhard, professor from Federal University of Bahia. So thank you, Dirk, for accepting the invitation.
Yeah, so, well, thanks for inviting me. So it's really nice to speak here. So today I would like to talk about the 2D anisotropic Kpz equation at stationarity. And so that's a joint work with Giuseppe Canizzaro from Warwick University and Fabio Toninelli from Vienna University. And however, this work is based on a recent work I did with Giuseppe together with Schönbau, who was a PhD student from London, but who left academia. And so that's why I decided to put him in here, because some of the things we use really rely on previous results. Okay, so I guess that maybe most of you maybe have seen at some point the Kpz equation, but I guess many of you are not familiar with the Kpz equation. So that's why I would like to spend the first few minutes of motivating the equation. So why it's a natural object to look at, so an interesting object to look at. Then I will talk a bit about it, and then I will come to talk about our results. Okay, so what's kind of the starting point? Well, probably one of the most fundamental questions in probability theory is the one of universality, right? Which essentially says, well, if you do a certain experiment many times, then the exact details of the models of the experiment shouldn't really matter. You can describe the outcome using the same distribution. And well, the first result that we all know is the central limit theorem for random variables, which is stated here, which essentially says that if you have a sequence of IID random variables with second moments, then this renormalized sum converges to the normal distribution with mean zero and a certain variance. And well, that's the central limit theorem because, well, the limit does not really depend on the xi's, on the details of the xi's, just on some kind of minor assumptions. So that's maybe the first big result one sees in probability theory. And well, as we all know, one can generalize this. So you can see this as a central limit theorem for a sequence of random numbers. Yeah. And now you can generalize it to a sequence of random functions or trajectories or paths. And that's usually called Donska's theorem, but which again is a CLT type of theorem, which pushes the first result a little bit further. So here you take a random walk on ZD, whose increments are I at D, have finite second moment, and then you can kind of define this random function. Well, you do it in the usual way. You look at the random walk at time nt, you center it, divide by square root of n. And so this object depends on t, so it defines a function, and it converges to a Brownian motion. And well, what the two results have in common is, in both cases, the limit is Gaussian. Yeah? And now you can ask yourself, well, okay, so I have a sequence of random numbers, and then I use fairly general assumptions they converge to something Gaussian. I have a sequence of random functions. Under fairly general assumptions they converge to something Gaussian. What is if I now go to a sequence of random fields or space-time functions? I mean, do I also see something Gaussian in a huge generality? And well, in this case, I don't know how to formulate such a general result, so I will focus on a specific example, but which allows me nicely to go over to the Kpz equation. So now what we want to do, we kind of want to formulate a similar result, but for random space-time functions. Yeah? And the result, the example I want to take is the one of the simple symmetric exclusion process. Yeah, the simple symmetric exclusion process. Maybe some of you know this process. If not, well, so what it is, so imagine that you're in the d-dimensional lattice, yeah? And now you put a bunch of random walkers on this d-dimensional lattice, and these random walkers do what random walkers do, they jump around. Yeah? And the exclusion process, the way they do it essentially independently of each other. However, subject to the exclusion rule, meaning that the two random walkers are not allowed to be at the same site at the same time. Yeah? So essentially, this exclusion rule imposes that as long as two random walkers are not nearest neighbor in the specific case, they don't know that the other exists. The the moment they're nearest neighbor, kind of they have a dependency because one is not allowed to jump on top of the other. Yeah. So just to explain this a bit more for those who see this for the first time. So let's think of the one-dimensional situation. So in particular, the exclusion rule implies that at time 0, at each side there can be at most one particle. Either there's no particle or there's one particle. So maybe you have a configuration at time 0 that looks like this. Maybe there's no particle here, no particle here, but maybe we have a particle here, for which I draw this kind of halfly filled circle. Maybe there's a particle here. Maybe there's also a particle here, but maybe there's no one here. A particle here, no particle here. Yeah. So let's look at these guys. Each of these particles is a simple random walk. So if you look at this guy, for instance, if you think of the nearest neighbor situation, then what happens is that to this edge and to this edge, there's an exponential clock attached. Well, this guy will wait until one of these two clock rings and jumps over the corresponding edge. So maybe the edge to the right rings first, so then this guy would jump here. So then the new configuration, let's see if this works, more or less, would be something like this. Yeah. So let's look at this guy. I mean, this guy also wants to behave like a simple random walk. So he will also look at the edge to the left, to the edge to the right, wait until one of these two clock rings, and then attempts to jump. So let's say the right edge rings first. So what he really wants to do, he wants to jump on top of this guy. But now the exclusion rule kicks in and forbids this jump. So this jump is not made. Yeah? That's the exclusion process. So if you think about it, I mean, so this thing evolves in time, right? And moreover, to each point of ZD, it associates the value 0 or 1, where 0 means, well, there's no exclusion particle, 1 means there's an exclusion particle. So that's really what we would call a random field, maybe. And so what we know is that the invariant measures are all given in this way, so they're product Bernoulli measures. So product Bernoulli for some fixed parameter rho, which here I will take between 0 and 1. 0 and 1 would also be allowed, but then it's kind of a boring invariant measure, because if rho would be 0, there would be no particle, nothing happens. If rho would be 1, there would be everywhere would be particles and nobody jumps. So these are kind of the interesting invariant measures. And now you can wonder, well, I mean, at the end of the day, what they're all a bunch of random walks. One random walk converges to something Gaussian. Does this whole thing converge to something Gaussian? If you rescale in the right way, and the answer is yes. So a result you could formulate could go more or less like this. So you look at this exclusion process, say the transition kernel of each of these random walkers is symmetric, yeah, having a finite second moment, and starting, let's say, from the invariant measure with mean rho. So the way to formulate is then this. So you would take a smooth, compactly supported function f, and you would define this functional. So let's check this functional out. So what happens here? So first of all, here we have f at position x divided by n. F has a compact support. Yeah, so let's think support of size 1. So this means f of x divided by n is 0 as soon as the norm of x divided by n is larger than 1. So the norm has to be less than 1. So this means in the sum there are roughly n to the d points. Oh, now we divide by this guy here. So we divide by the square root of the number of points. So there's the central limit theorem scaling that we have here. And then what we essentially do, we essentially weight this function with this ether, but accelerated, where time is accelerated by a factor of n squared. So time is accelerated by n squared, and space is scaled by n. So that's the typical diffusive scaling that we see from the random walk also. And last but not least, the thing would not converge, so that essentially we need to center it. It's the same that happens in the usual center limit theory. Yeah. And what the result is, so this yn converges, and it converges to something Gaussian. Yeah. So now we essentially saw 3 examples where you see something Gaussian. So kind of this is evidence of the fact that the Gaussian universality class is huge. Now you can ask yourself, is there something else And the second question is, how stable is the Gaussian universality class? With how stable, I mean, if we now would perturb this model a little bit, so we kind of would slightly change it. If the Gaussian universality class were stable, this would not really change the outcome. The limit would be still the same. So where can you play a little bit with this model? Where can you perturb a little bit this model? Well, I mean, here we assume that we have a symmetric transition kernel. So now you could ask yourself, well, what is this? What happens if I'm not in a perfectly symmetric situation, but it's almost symmetric? Let's say there's a weak asymmetry that vanishes in the limit. I mean, naively, it shouldn't really change much because we are interested in the limit. The asymmetry vanishes in the limit, so what possibly could happen? However, what happens is actually that, well, everything changes. So if you have a slight asymmetry of this order, 1 over square root of n, it turns out that the limit is not Gaussian anymore, but it's different. And this is not something that is a particular feature of the exclusion process, but there are other models where it turns out that the limit is not Gaussian. Yeah? It doesn't really matter what these models are, but there's a certain class of models where the limit turns out not to be Gaussian anymore. And what we will see in a minute is that essentially this slight asymmetry induces some kind of a certain non-linearity that you don't see in Gaussian models. Yeah? So just to be clear, what do I mean with non-linear, asymmetry of order 1 over square root of n? So if you recall this picture of the exclusion process, say with a guy here, with a guy here, with a guy here. So, I mean, then I was saying that here and here with exponential clocks and here and here with exponential clocks. What I didn't mention, but I was assuming implicitly, is that both of them have rate 1. Right? In this case, I would be in a perfectly symmetric situation. Asymmetry of order 1 over square root of n really means that I increase or decrease one of the two rates by something of this form. Yeah? So now it's a little bit more likely to jump to the right, but I mean only a tiny bit more likely. Yeah? But again, it turns out that the limit really changes dramatically. Okay. So let's check out what is this limit. And so this limit is what is often called the Kpz equation. It's always called the Kpz equation. Yeah. So now let's come to this. So what is this Kpz equation? It's this object. So let's look at it very carefully. So first of all, what do we search here? We search for a function h that depends on time and on space. All right. So how is this function h given? Well, on the left-hand side, we have the time derivative, right? So we kind of want to quantify how this function h changes in time. We change t by a tiny little bit. And what it says, the rate of change in time is given by the sum of 3 terms. So we have the Laplacian term, we have a noise term, and we have a non-linearity. So why is non-linear? Well, the gradient of h appears twice in an inner product, so that's morally something like gradient h squared. Okay, so let's look at all of these 3 terms separately to understand them better. So first of all, we have the Laplacian term. So what is the effect of the Laplacian in an equation? So what is kind of known in PDE theory is that to assume that your solution looks something like this, very rough, very rough. Yeah. And now you put in a Laplacian into the equation. So you get the Laplacian into the equation. The Laplacian has the effect of making the solution more smooth. So if you put the Laplacian in, yeah, so that's not very beautiful. The Laplacian would kind of make this thing very smooth. I'm a bit exaggerating here maybe, but this is morally what happens. Again, if you know PDE theory, then it's maybe nothing new. However, if you don't know PDE theory, there's a way how to understand it from a probabilistic point of view. So think of Brownian motion. Think of the transition probability, transition kernel of Brownian motion. This 1 over square root of 2 pi t exponential minus x squared over 2t. Yeah. So if you think about it, at least for t positive, it's a perfectly smooth function, right? You can calculate all of its derivative in time, in space, as long as t is positive. That's all its derivatives. Yeah. And if you think a little bit more, I mean, if we denote by k this transition kernel, then it satisfies this equation here, right? Where the initial condition is what? Well, if you send time to 0, it would be something like a Dirk of 0x, which essentially means it's infinity at 0 and it's 0 everywhere else. So even though at time t equals to 0, you start with something that is not smooth. It's not really, this thing is not really differentiable. You put in the Laplacian, immediately when you turn on time for t positive, you get a perfectly smooth function. So that's one way to convince yourself that the Laplacian smoothes out things. Okay, so that's the Laplacian. So now let's come to the noise. Yeah, so this Kpz here. So this Kpz is what's called space-time white noise. So what is this? It's first of all Gaussian. It has a mean 0. And so how are the correlations? What is the covariance function? Well, it's something like this. So psi of tx, psi of sy is Dirac in st and Dirac in yx. So what does it mean? So this simply means that as long as the space-time point tx is not equal to sy, this expectation is 0. Yeah. So essentially what it really means is that what you really do is that on each point in space-time, to each point tx, you associate a Gaussian random variable with mean 0. And all these Gaussian random variables are independent. Yeah. So in particular, from a probabilistic point of view, it's a very nice object, right? Because first of all, everything is Gaussian, so we have a lot of experience with it, and everything is really independent. So it's a very nice object to work with from a probabilistic point of view. Yeah. So that's the noise term. And last but not least, with the non-linearity, right? So it's this term here. So where the gradient appears twice. So if we think again, so what was the gradient of the function geometrically? So the gradient of the function h always, at a certain point x, always points in the direction of the strongest increase. Yeah? So in other words, the gradient is kind of a function of the slope. And it gives you some idea of the slope. So in other words, the non-linearity, since it depends on the gradient, is a function of the slope. Yeah, so slope-dependent growth or decrease. Yeah, and then finally with this Q here with this d by d matrix. So dimension 1 is this number, so you can absorb into lambda, but in dimension 2 and higher, it's a proper matrix, and it kind of modulates the way the slope dependence acts. Yeah, that's a way to picture. Okay, so that's the equation. Okay, so let's continue. So again, essentially just a repetition. So it's smoothing mechanism. So the larger this number informs the Laplacian, the stronger the smoothing effect. The Q, as I already said, is slope dependence. Yeah, so kind of modulates how I want the slope dependence to act. D is the strength of the noise, right? So the larger this term here, the stronger should be the effect of the noise. And finally, lambda is the strength of the nonlinearity. So for what comes, I don't want to play with all of these parameters, so I will fix nu and d, and I only keep lambda and q. Yeah. Okay, so that's what we'll do. Well, now you have an equation. So the first thing you want to do with an equation, you want to solve the equation, afterwards study maybe some properties. And unfortunately, here's kind of the, well, one of the big problems is that it's not immediately clear what it means or how can you solve this equation. So why is this so? So remember, I said that the white noise Kpz, so it's essentially Gaussian at every space-time point, but everything independent. It's very nice from a probabilistic point of view. We can calculate easily probabilities. But from an analytical point of view, and that's a property that you need, some analytical property when you want to solve an equation, it's a very bad object. Why? Well, so imagine that you look at a very small box in space-time. Well, how many points do you have there? Uncountably many. Now, the probability that a Gaussian is larger than 10 trillion may be small but positive, and that smaller than minus 10 trillion may be small but still positive. Now, if you have uncountably many independent guys, well, the value 10 trillion, you will see uncountably often. Yeah. And no matter how large the value is, I mean, some of these Gaussian guys will be larger than this or smaller than this. Yeah? And this kind of happens in a completely decorrelated way, meaning that just because one value is large doesn't mean that the neighbor is small. It doesn't mean that the neighbor is also large, so it may be kind of completely small. So if you think of it of size or as a continuous function or not, it turns out not at all. So it turns out not to be a function at all in the usual sense. So here's some kind of a simulation from Wikipedia of a one-dimensional white noise. Yes, you can see a bit the discreteness here. And what you really can observe is that maybe there's some big peaks, but next to the big peak, there's not necessarily another big peak. So the value may drop drastically. So if you're interested in smoothness properties of this function, it has very bad smoothness properties. Yeah? And that's kind of bad, because if we look again back at this equation, and if we for a moment ignore the linear part, this equation you can solve, there's a formula for that. Then you can check what is the regularity of the solution, how smooth is the solution, and the answer is this. Actually, there's a minus missing here. This minus d over 2 plus 1 minus. So dimension 1 would be almost 1/2 Hölder, like Brownian motion. In dimension 2, it would be less than 0 Hölder. In dimension 3, minus 1/2 Hölder, actually a little bit less. And if there's a negative regularity, this really means it's not a function anymore. It's a generalized functional distribution. However, already in dimension 1, where this guy is essentially 1/2, the regularity of the gradient would be minus 1/2. And now there's a general theorem from analysis which tells you, well, if something has a negative regularity, then there's no way of squaring it in a natural way. So it's a result. It's not that we don't know how to square it. It's the result that there's no kind of canonical way. Canonical in the sense that, or if you would now approximate this guy by smooth guys, then you can do the product as usual, as we always do, and then remove kind of the regularization. Then either the limit may not be unique or this approximation explodes. That's what it means. So it's not so clear how to solve this equation. So the first step around this is to look at some regularized version of this equation, and then maybe check what happens when you remove the regularization. Okay, so still that's live. So this you have to accept that first you need to look at something that's a bit more regular, and then you remove the regularization. So what kind of things are we interested in? Well, we are interested in large space, large time scales, and we would like to check how's the behavior of this equation. And in particular, does the non-linearity really matter? With that, I mean the following. So remember, I told you that if you take the exclusion process and you introduce a weak asymmetry, then formally you arrive at this Kpz equation. But now I told you that this equation is actually not well defined. So it may be that, well, if you do the formal calculations, then it seems that there's some kind of nonlinearity there. But if you really look closely, this nonlinearity is actually 0 and it's not really there. So maybe the asymmetry is so weak that at the end of the day, the nonlinearity doesn't really matter. Yeah. So that's kind of the question we have in mind. Is the equation really as it is, or is it maybe wrong to write the nonlinearity there? And how can you start to investigate this? Well, first you look at the linear equation. Yeah? You study the linear equation. And one thing you can look at, which is always useful, is you can check, is there maybe a rescaling under which the equation is scale invariant? Yeah? If there's one rescaling, Then you apply the same rescaling to the nonlinear equation and you see what happens, and you hope that you can deduce something from that. And that actually turns out to be very useful. So it turns out that if you look at this rescaling, under this rescaling, the linear equation is invariant. So it kind of, this H epsilon satisfies the same equation, at least in law. So just one remark. So I was saying I want to look at large space-time scales, and that's really what happens here, right? If here I send epsilon to 0, so t divided by epsilon squared goes to infinity. So I really look at large time scales. And same thing here, if I send epsilon to 0, x divided by epsilon goes also to infinity, right? Really look at large space-time points. Yeah? Okay, so that's also diffusive scaling. So now let's plug this into the equation. I will not do the computation here, so you need to trust me. And that's what you would get. Yeah? Okay. So the first observation is here there's nothing. Here there's nothing. And that's not super surprising because I told you that under this scaling, the linear equation is invariant. And well, these are the only two terms that are there in the linear equation. So with linear equation, I mean lambda equal to 0. However, in front of the nonlinearity, there's something, right? There's an epsilon factor. And now the first thing you can do is, well, how does this guy behave? So you try not to work out this exponent, d minus 2 over 2. For d equal to 1, you get minus 1/2, right? For d equal to 1. For d equal to 2, you get 0. Equal to 2. And if d is 3 or larger, the thing is simply positive. Or 3 or higher, this power is positive. So what does this mean? As epsilon tends to 0, in dimension 1, the factor explodes. In dimension 3, the factor goes to 0. In dimension 2, nothing really happens. The equation is scaling around. So this suggests that there are three regimes. The one-dimensional regime with the nonlinearity really should matter, right? Because it formally explodes as epsilon goes to 0. The three-dimensional high-dimensional regime with the nonlinearity should not really matter because as you send epsilon to 0, formally goes to 0. And then the marginal case. Yeah? So this is what it really suggests. Okay. And at least for d equal to 1 and d at least 3, it really turns out, well, that's correct. So for d equal to 1, this essentially has been confirmed. But just let me make one remark. So, I mean, for d equal to 1, there's been a lot of activity in the last years. And actually, it was possible to give a meaning to this equation, but only in short space-time scales. It turns out that if you want to look at this relevant question for d equal to 1 large space-time scales, then it turns out that this is not the correct scaling. So there's a different scaling called 1, 2, 3 scaling. And if you use this different scaling, it really turns out that the equation converges to the so-called Kpz fixed point in the nonlinearity meters. It has been partially confirmed that this picture is true in 3 or higher dimensions. However, only the case where Q is some beta times the identity matrix, so the matrix that has ones on the diagonal, for beta small. Now there's some kind of mathematical issue we need to prove it for different matrices. And well, then there's a marginal dimension, which has been open for a long time. And that's the case I would like now to focus on. So let's check the marginal dimension. And there has been some activity by physicists. And what they conjecture is that there are actually two regimes. There's the so-called isotropic regime and the anisotropic regime. And the distinguishing feature between these two regimes is supposed to be the determinant of Q. So if the determinant is positive, that's the isotropic regime, which includes the identity matrix. Then what's conjectured is that the nonlinearity really should matter, in the sense that if you look at these two lines, so the first line tells you that the variance of h of t0 minus h of 0, 0 grows like t to the 2 zeta for some theta which is more or less 2.04 for large t. And if you fix t, and you look at the variance of h of tx minus h of ty, then it should correlate x minus, like the distance of x and y to the 2 alpha, for some alpha that's roughly 0.39. So these are some values you get from numerical calculations. Yeah. And why do I say that? Well, this means that the nonlinearity should be relevant. Well, if you compare to the linear equation, then you get complete different values. In the linear equation, you would get some logarithmic growth here. Yeah? In the linear equation, formally belongs to the anisotropic class. Yeah? So where the determinant is 0, which allows also q to be equal to 0. And in this case, it's conjectured that this happens. Yeah? For whatever q in this class. Yeah? So we should have the same behavior as for lambda equal to 0. Okay. Now let me explain to you what we know. So I will first go to the isotropic case. Yeah. And so the isotropic case, again, so mathematically what has been done is to choose q to be the identity. In this case, the nonlinearity is the gradient h squared. Yeah. And what is this here? So I told you that the equation is not well posed, so you can't really directly work with the equation. So you need to regularize the equation. So this phi epsilon here. So first we start with the phi, which is a smooth bump function, say positive, integrating to C infinity, compact support. And then you rescale it. You convolve it with psi. So you get something smooth. That's something you can show. And now, if you choose phi correctly, as epsilon tends to 0, the thing really approximates the white noise psi. So it's an approximation of the real equation. Okay. That's something you can study. However, mathematically, it turned out that it's not easy. And one thing that has been done, instead of fixing lambda, sending lambda to 0. Yeah? In a smart way. So what does it mean? So what we really do, we really look at lambda of this form. So we divide by square root of log epsilon to the minus 1. If you think about it, so this means that this factor in front of the nonlinearity tends to 0. Yeah, so you kind of weaken the way the nonlinearity acts. And what they found out was that if you choose lambda not too large means smaller than square root of 2 pi. If you center h epsilon, right, that's always what we do when we try to prove a central limit theorem, we center. Then the thing turns out to converge to what? To such an equation. If you now compare to the equation above, it's almost the same equation, but without nonlinearity and maybe with a prefect in front of the noise. Yeah? So it really looks like the linear equation. However, now remember that I was saying that it was conjectured that in the isotropic case, the nonlinearity should matter. And now I give a result where, well, the limit, the nonlinearity vanishes. So this may be contradicting. However, it is not. Because what is known is that this thing converges to infinity as lambda approaches lambda hat. So as lambda approaches lambda hat, the strength of the noise blows completely up. And, well, we don't really know. I mean, there's no way of writing down such an equation. The equation must change. Yeah? So since what they really did, they kind of figured out what does need to be the strength of the constant in front of the nonlinearity such that you just see the effect of the nonlinearity. I mean, what is expected, of course, if you send the constant in front of the nonlinearity super fast to 0, then, well, at some point it shouldn't really matter much anymore. But which they really showed is that, well, if you already take it of that form, lambda divided by square root of log of epsilon to the minus 1, and if lambda is close to square root of 2 pi, maybe is square root of 2 pi, at this point the behavior really should change. So they kind of confirmed this picture. Of course, we don't know what happens beyond this value, but it's very suggestive. Okay. And so why did they use this choice of Q, the identity matrix? There's a trick called Kohl-Hopf transform, which allows you to go from this equation to a more linear equation, which turns out you can treat. That's also the reason why they choose in D larger equal to 3 cubing the identity matrix, so that you can make this transformation. Okay. So let's go to the anisotropic case. So that's where we worked on. Okay. Okay. So what should you expect in the anisotropic case? So there has been more activity by physicists, actually. So that's the paper where they did some numerical simulations. And so their findings were that entirely consistent with Rowe's prediction, an anisotropy that involves a change in sign or the vanishing of one of the non-linearity parameters incurs a very rapid, unrelenting, and nearly immediate crossover to the Edwards-Wilkins fixed point. So what do they mean with change in sign? So this means that they think of a lambda, of a Q, just of that form. So in particular, the determinant is negative if the signs of lambda 1, lambda 2 differ. And what is Edwards-Wilkinson? So that's simply another name for stochastic heat equation, which is another name for linear equation. Yeah, so they expect kind of that you go over to the linear equation, and well, essentially the same was written in a book by physicists some years later. So thus, if the signs of the two lambdas are opposite, the non-linearity is irrelevant, and the scaling is described by the linear Edward-Wilkinson equation. Yeah. So this means there's some kind of agreement in the physics literature, and so you can kind of try to go after that and try to prove or confirm it mathematically, right? However, as always, we're not able to deal with a completely general case, so again, we need to make a very specific choice, which is this matrix here. So diagonal of 1 minus 1. Then what turns out, the non-linearity is of this form. So you subtract the two derivatives, or the two squares. Yeah? And the first thing that you observe is that this kind of Kohl-Hopf transform that takes the equation, maps it to an equation that you know how to deal with, does not seem to be available anymore. So that's bad. However, the good news is that we know its invariant measure. That was something that we did in the work with Philip. So we know its invariant measure, which is a so-called Gaussian free field. It doesn't really matter what it is, but what is important is it's explicit. That's explicit. And that's a feature that we use a lot. So that's really the equation we want to look at, and we want to check the conjecture of the physicists. And as I said, well, this equation as it stands doesn't make perfectly sense, so you need to smoothen something out. You need to regularize something. And there are two choices, essentially. Either the noise or the nonlinearity. And in this case, we chose to regularize the nonlinearity, and it turns out everything is well defined. Because if you do it in this way, the invariant measure doesn't change. So what I will show now may look scary. So let's see. So the real equation we look at is this guy. So the first thing is still the Laplacian. The last thing is still the noise. But in the middle, there's this N1H here. What is N1H? So it's written here. So what do? You take your H. And then you apply a certain pi1 to it. So what is pi1? Pi1 is the cutoff in Fourier space. So what do I mean with this? So if you're on a torus of size L, what you can do is you can write your H essentially, let's do like this, essentially in this form. So here's some coefficients HK, and here EK, where EK are basis vectors. Yeah, so what then the pi1 does of H, it takes the same thing, yeah, but requires that K has a norm smaller than 1. HK, EK. Yeah? That's what it does. Because kind of all the irregularity comes from the large Ks. And so just as a reminder, so this K here actually is of this form. You need to think of it's this form, right? It's z divided by L squared. So the number of terms in this sum is of the L squared. So that's what it does. So you apply the pi 1, you take the derivative, you square it, and then turns out that the sum Fourier component is larger than 1 again, so you cut off again. That's what it does. That's the way of regularizing. Okay. And then essentially what we want to do, we want to take the size of the torus to infinity. So in this way also the number of Fourier components you consider also goes to infinity and then epsilon to 0. And you can convince yourself that then formally this limit should coincide with this equation. Okay. Okay, so let's continue. So what, of course, we would like to know is, we do this diffusive rescaling. Yeah? Does this H epsilon have the same qualitative behavior as L goes into infinity, so the size of the torus, and epsilon to 0, as the stochastic heat equation? So as the equation where lambda is equal to 0, the linear equation. Yeah, so I mean, at least how we understood the physicists is that's what should happen. However, the answer is no. Yeah. And a kind of an informal way of formulating it would be like this. So as soon as lambda is 0, so as soon as there's a non-linearity, so this process H epsilon evolves non-trivially on timescales of this order. If you think about it, log epsilon to the minus delta goes to 0. So it evolves non-trivially on very, 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 very short timescales. Yeah? And it has a correlation length of this form, square root of t times log t to the delta half. So not diffusive. Yeah? So why does it lead to the answer no? Well, so what happens to the linear equation? So the linear equation actually is scale invariant, right? That's how we chose the scaling. So the linear equation, if epsilon is positive or 0, it doesn't really matter. It's always the same object. Yeah. So the way the linear equation evolves does not depend on epsilon. So the timescales do not depend on epsilon. Yeah. And moreover, the correlation length in the linear equation is order square root of t. So it's diffusive. Or square root of t times some log factor. Yeah. Yeah. So that's kind of the important remark. So in the remaining time, maybe I would like shortly to explain what I mean with this. I mean, it's not completely formal. So first of all, what does it mean to evolve non-trivially? I mean, there are 1,000 ways of measuring it, and it now depends on what kind of way you are able to treat, to analyze. And so what I will present now is not the way how we formulated the main result in the paper, but it's the consequence, so it's rigorous. Yeah. So non-trivially, for instance, could mean the following. So what you really do is you look at this kind of rescale or normalized covariance. So if you look at it, so in the numerator you have covariance of ht, h0, denominator covariance of h0, h0, so the variance. And evolving non-trivially on this time scales now means the following. If you take a certain test function, so this condition has something to do with the invariant measure. Yeah. You take a certain test function, then uniform in epsilon, for some a, this normalized covariance is smaller than 1. For some t, less than this value. So, and again, log epsilon to the minus delta really goes to 0. And why is it now different from the linear equation? So remove this. So in linear equation, of course, as soon as t is positive, this ratio may also be smaller than 1. But the point is that in the linear equation, this a may really or will depend on epsilon. Yeah. So if you choose t of order epsilon or something like that, this a may be smaller than 1, but depends on epsilon. And as you send t to 0, this a really converges to 1, which is different from here. Here you can really find a sequence of times that go to 0 with epsilon, such that you really observe always the same a. Yeah? So that's one way of seeing it. And last but not least, so the other thing I was talking about is something called the correlation length. So what do I mean with this? Well, again, if you think of Brownian motion, and if you look at the transition probability of Brownian motion, you can see that it's diffusive. Yeah, so it has this kind of square root of t diffusivity. Yeah. However, how can you in general measure correlation length? And well, that's something that we borrowed from the literature. We didn't come up with this. So if you think now of a particle, so forget all equations, you think of a particle that's moving around. Yeah. And now you would like to know, well, does it behave diffusively or not? How can I measure this? Well, one way is, let's call it xt here. That's the origin. One way is you are able to compute the transition probabilities and then you read it off. But not always you're able to do this. So one way of measuring it, and again, so we didn't come up with this, is look at so-called bulk diffusion. So what is this? So it's something that depends on time. So what you really look at, you look at some kind of a second moment of this st of x. Yeah. Again, if you think of Brownian motion, the result would now be t times some factor of pi. Yeah. So in particular, if you think of Brownian motion divided by t here, then this thing is actually now constant in time. Yeah. Which is really due to the fact that Brownian motion behaves diffusively. Yeah, so that's one way of measuring diffusivity or not. And now essentially what we want to do the same in our context, but unfortunately we don't have one particle that is jumping around. But we have some kind of equation, some kind of field. So how do you do this? So essentially what you want to do is you want to kind of get some kind of equivalent of this st of x. Yeah, so in particular what you would like is that you would like to have something that kind of starts from a point. Yeah? And I will shortly explain you how to do this. So, and it should have something to do with correlations, of course, right? It should not be completely arbitrary. And one thing of doing it is that instead of h, it turns out it's slightly more convenient to look at this. So what is this? Half Laplacian of h. So the way how you calculate the half Laplacian is you calculate the Fourier transform of this h, and then you multiply each Fourier component with k. So since half Laplacian is a multiplication operator, so it's kind of essentially gives an equivalent between h and u. Yeah? If you know h, you know u. If you know u, you know h, up to the zero Fourier component. And what turns out, this u has also a bar measure, which is white noise. Yeah? So it's kind of trivially correlated. Yeah? And then in our context, and again, we copied it from the literature, this part, you can define something like this, so essentially some kind of a correlation. Yeah, and it turns out it has all these nice properties, this property, and you can kind of now copy this, this definition. If you do it for the linear equation, it turns out that this d of t does not depend on time, actually it's constant, yeah, which really means that the linear equation behaves diffusively. If you do it in our case, it turns out that the thing explodes. Yeah, it's kind of a way of formulating this result a little bit more rigorously. So if you first send L to infinity, this diffusion coefficient essentially is between log t to the delta and log t to the 1 minus delta, which again is something that does not happen in the linear equation. So this way you kind of create two observables that distinguish this anisotropic Kpz equation from the linear equation, which was kind of surprising for us at first. Okay, so I think I would like to stop here.
Thank you, Dirk. Do we have any questions or comments?
I have one question. First of all, thank you for the nice seminar. My question is: you started with the exclusion process, and I mean, does your result say anything about that process, the exclusion process? I mean, I suppose in the asymmetric case, right? I mean,
yeah. So this would be the asymmetric case, but unfortunately, the answer is no. So when you look at the Kpz equation, for now there's some discrete models that are conjectured to converge to the Kpz equation, but nothing of this has been proven yet. So this was part of the motivation to really first look at the limit, and then maybe you can kind of extract some properties that discrete models should have. Because usually looking at the limit is usually easier than looking at the discrete models. So next task would be really to go to discrete models and see if they have similar features. Yeah. But maybe one comment I can do. So our method of proof was very much inspired by the method of Yao, who started the asymmetric exclusion process, where he figured out this diffusion coefficient is of the order square root of t times log t to the 2/3. And it turns out a similar method also works in this case. Yeah.
Do you have any other questions or comments? I have a small, maybe curiosity. Can you say something about why you need exactly your Q as -1 and 1? Because you did some comments that it works only in this specific case.
Yeah. Yeah, so you're completely right. So what we heavily rely on is that we know the invariant measure. Because there's a method introduced by Patissa Gonzalez and Milton Jada. It's called energy solutions, and it kind of is always lurking in the background, and it relies on the knowledge of the invariant measure. And
it's because there's no invariant measure, or it's because you don't have explicitly a form for it?
Well, we don't, yeah, if you change this matrix Q, then we essentially don't know anything.
Okay.
Not invariant measure. So essentially what you can do is you can either take this matrix Q and any rotation of it. And in this case, it would still work.
Yeah.
So this would do, but this of course somehow the same matrix. But if you would go to something different, I mean, even if you would go to something like, say, 1, I don't know, -1 minus epsilon or something like this, it destroys the invariant measure. This would be kind of natural next choice. And there's some work by Milton Jada on discrete models where you only can guess the invariant measure, but it's not so clear for me how to apply this.
And that's the same reason why you choose to not work with this third term, right? This your noise in some sense, because you lose the invariant measure.
Yeah, exactly. So if you exactly. So in this case, if you would truncate the noise, then you would be able to. So so then I think what would happen is that I'm not sure. Maybe you would keep the invariant measure, but the invariant measure would depend on the regularization on epsilon. Yeah, essentially on epsilon. Yeah.
Do we have any more questions or comments? If not, let's thank Dirk again, please. And on your mic. Thank you, Dirk. Very nice.
Okay.
So, you know, this is not related specifically with your theorems, but other limit theorems for exclusion process with rate different from root of n.
Yes. So there's essentially three. Where is it? So there's essentially three regimes in this process. So there's one where the asymmetry is weaker than 1 over square root of n. Then you there's one where it's of the order of 1 over square root of n, then you get this Kpz equation. And then if it's larger than 1 over square root of n, then you formally should get the Kpz fixed point.
A fixed point, okay.
Yeah. But this, I mean, partially it has been proven, but I don't know. I mean, there was a paper that recently appeared. I think if you take an asymmetry of a fixed order that does not vanish, then we know that it's true. But if it still vanishes, then I'm not completely sure. Then I don't think it's known.
Okay. Thank you. Oh, I didn't stop the recording.
Okay.